Hello, I'm Steve Lewis. Welcome to the fifth module of Applied Statistics for Healthcare Data Analysis. This course is funded by a grant from the United States Department of Labor and uses a curriculum developed by Carnegie Mellon University. We're using a model of statistical analysis that involves four phases: capturing data from our population about variables of interest, subjecting those variables to analysis to generate descriptive statistics, conceptually, but not operationally, applying the principles of probability to those statistics, and then, fourth, drawing inference about the corresponding parameters in our population based on the probabilities associated with our sample statistics. Today we're going to move into that fourth area, inferring the parameters of our population from our sample statistics. Now, in the probability modules, we captured two particularly important ideas. The first was that if we took a very, very large number of samples or trials of our variable from our population, the sampling distribution of those variables, in other words, the way that the variables' values distributed themselves from one sample to another across the entire range of samples we took, would begin to approach or mimic the way that variable distributed itself in the population as a whole, so that the statistic that we got from that hypothetical range of samples, that sampling distribution, the statistic associated with that sampling distribution would mimic the parameter or the value of that variable for the population. And this would be true of a proportion for a categorical variable or a mean for a quantitative variable. The second idea that we captured from probability was that this sampling distribution that we imagine is normally distributed. In other words, the mean of means of a quantitative variable in a sampling distribution is the center of a symmetrical distribution which follows the rule of the standard deviation, so that a predictable percentage of the events, in other words, the means of all of these many imaginary samples, fall within the predictable standard deviation distribution, that roughly 68% of those events occur within one standard deviation of the sampling mean, the parameter, that roughly 95% fall within two standard deviations, and roughly 99.7% fall within three standard deviations on either side of that mean. And that's true also when we're talking about a categorical, a categorical variable for the proportion associated with that variable. So armed with those two concepts, we can start to think about the relationship between our sample statistic, our sample proportion, or our sample mean, depending on what kind of variable we're looking at, and the corresponding parameter in the population. Now, of course, in reality, we didn't take a large number of samples. We took one sample. But what enables us to think in terms of a sampling distribution is the method by which we took our sample. This goes back to our very early conversation about the importance of building our statistical analysis and the sampling to generate the data to support that analysis, building those elements into the basic design of our research project or our investigation. We're at the point now where we can only draw inference about the parameters in our population from our sample statistics if, first, we can be sure that we drew our original sample randomly, that every event in the population had the same chance of being included in our sample as every other event. And second, that our sample is large enough. And if we're talking about a proportion of a categorical variable, that both the proportion and the remainder of the sample, the rest of the distribution net of the proportion, each have at least 10 cases. Similarly, if we're talking about the mean of a quantitative variable, that the sample includes at least 30 cases and is, again, randomly selected. If our sample meets those two criteria, then we can apply that concept of a sampling distribution to our sample statistic in order to support inference about the about the parameter. And the tools that we will be using to test a statistic for that purpose all are built on those two assumptions and on the assumptions around the probabilities associated with a sampling distribution. Now, we're going to be looking at two different kinds of inference testing. The first is simply estimation of a parameter's value. And the simplest form of estimation is what we call point estimation, simply taking the value of our statistic as the value of the corresponding parameter in the population. This is simple, it's intuitive, and it meets a lot of very basic research needs. It's also conceptually supported by the idea of the law of large numbers. Remember that when we assumed that there have been a very large number of samples taken about our variable from the population, that the larger the sample is, the smaller the spread of the distribution of the results of those samples. What that means in terms of being able to infer the parameter of a value, the parameter of a variable from our sample statistic is that using the concept of a sampling distribution enables us to assume that the opportunity for our sample statistic, whether a proportion or a mean, to vary from the corresponding parameter in the population is reduced. It's a very narrow range of opportunity. And I think some of the exercises in the unit of the curriculum about probability illustrated that point, that the larger the sample is, the narrower the spread of its distribution. Getting back to estimation, a more rigorous and more robust version of estimation is called interval estimation. And there we're looking at the question of how confident we can be that the relationship between our sample statistic and the corresponding population parameter is. And there what we do is take the standard deviation of our sample statistic, because we know that there's a specific probability associated with an event being within a given number of standard deviations or fractions of a standard deviation from the sample statistic. So if we want to know, for example, what the 95% probability is of the place of the parameter value, we can take two standard deviations below and two standard deviations above our sample statistic, our proportion or our mean, and say that we can be 95% confident that the corresponding parameter for the population falls between the value that is two standard deviations below and the value that is two standard deviations above that statistic. Now, estimation, not only point and interval, as I said, serves a lot of practical day-to-day research needs. But there are certain research questions that require a more nuanced look at the parameter and its relationship to our statistic. And for that, we use a technique called hypothesis testing. A hypothesis is simply a statement of a proposition. And what we do is explore the relationship between two competing hypotheses. The structure of hypothesis testing somewhat parallels the model of statistical analysis we've been using. We posit two competing hypotheses. We collect data to support analysis about those two. We perform analysis to create a test statistic and examine the probability associated with the value of that test statistic. And then we draw conclusions about the relationship between the two hypotheses based on our research question. So it's largely a four-step process. Now, the key to this is to ensure that we have structured our hypotheses correctly. We have basically two hypotheses in every test. The first is a baseline, or you can think of it as a stalking horse, which we call the null hypothesis. And it states that if we're looking at one particular variable, there is no difference between two versions of those variables. They are going to have the same value. An alternative hypothesis, which is what we really want to know about, if you will, is that there is a difference in two versions of the same variable, or that there is a relationship between two different variables. Whereas the null hypothesis in that case would be that there is no relationship between the two variables and they represent the same population. So the structure of our two hypotheses is critical to the success of hypothesis testing. The null hypothesis always has to state that if we're looking at one variable in two different iterations, those two iterations are the same. They have the same value. That the alternative hypothesis, though, can have various versions. For example, if we have a medical practice where we have introduced a patient education program for self-management of asthma, and we want to know whether the rate of emergency department crisis visits for asthma has changed because of, or after we introduced that particular intervention. The question is whether we just want to know if there's a change or if we want to know the directionality of that change. We would hope, for example, after we've made the investment in that intervention, that the rate of these emergency department visits declined. And so we would want to structure our alternative hypothesis to say that the rate declined. Our null hypothesis would say the rate stayed the same. Our alternative hypothesis would say it declined. If we did not have a particular reason to suspect or to want to know which direction occurred, then we could simply structure our alternative hypothesis to say that the rate of emergency department asthma crisis events is different after the intervention from what it was before. So the structure of the two hypotheses, as I say, is critical to ensuring that we can do a useful test of inference. The second point is that the particular tools that we will use depend on the relationship between the between the variables, if we're looking at two variables, or the nature of the particular variables involved. Getting back to our early discussion about the different classes of variables. where we talked about categorical versus quantitative and explanatory versus response variables. The particular inferential tool we're going to use is a function of whether we're talking about a single categorical variable or a single quantitative variable, whether we're talking about the relationship between two categorical variables or two quantitative variables, or between a categorical explanatory variable and a quantitative response variable. In this particular course, we're not going to be looking at relationships between a quantitative explanatory variable and a categorical response variable. That involves substantially more mathematics than I feel comfortable with, and that I think it's reasonable to expect of you folks at this point. So at this point, I'm going to drop it and encourage you to have a look at the particular relationships between the classes of variables we're going to be dealing with and which inferential analysis tools we're going to be using. There are good crib sheets, if you will, on page 172 and 180 of the curriculum to help you look through those differences. Thank you very much, and I look forward to seeing you next time.